Right, so it's looking at what state the car is in, plus what is the question?
If there's a way that the decision process is able to correlate to key value stores, so two vehicles that are next to each other that are storing values about their state.
Right, yeah, so the key value store has the state of each car. So the very cars have their state variables, so each car has its location. That's one part of the state. The other part is the learning part of the state is that what are the weights, the Markov it turns out that as we're doing simulation, we're keeping track of how much time do we spend in each states. So we're running simulations on the CPU to have the cars interact with each other, and then we're recording how much time each car is spending in each of the states as it goes through this process, and then we're penalizing when an accident happens in that simulation. We might update the values back to the state store, which is these probability times and weights, and then the system starts a new instance of the simulation where it picks up on what was last learned. So this notion of continuous learning. So whatever the last best learned model was, we pick up from that, and the next simulation uses that as its forward-going path. We have several different parallel simulations running, so whenever a simulation ends, it picks up the best state, simulates with that, and then at the end of that, it had a positive outcome that writes those states, it updates the Markov model back. Oh, okay, that's good. All right, so hopefully is that so this notion of simulation and learning where we're attempting to drive the car, making decisions on this actions based on what state we're in, and rewarding states that lead to this, seeing how long we spend in states and updating the time that we spend in states. And then doing that. And then the learning process is retrieving how much time we spent in states, correlating that to probability, computing the next best action, then updating our action table that gives us the best reward. And so it's a continuous learning process where it keeps getting a little bit better. So this is it. So this is when we first start the simulation, this is what it looks like. So this is about 1 minute into the simulation. And each of the 30 cars now has just been learning a little bit. You can see it's a little bit erratic at this point. The blue car, we're at the viewpoint of the blue car. The blue car could be any of the 30 cars. It's all the same. So you can see from his point of view, this is what the world looks like. This is what's around him. And so you can see he's a little naive, bouncing back and forth. He's learned not to hide into a car right away. But now when the car changes color, that means that somewhere else in the simulation, somebody had an accident. Because anytime that it ends, it restarts, and you'll notice it by the car changes color. So any accident of any car in the simulation will cause it to restart. And you can see that this is pretty wild. It's like this is beginner driving. And that was almost the rear end, and that was, you just got your engine right there. And so, let me, just to show that one more, let me go back and so again, is that this is early on in the simulation. The cars don't have a lot of training values yet. They make decisions that are a little bit erratic, like changing lanes and we don't need to. Why not? It's not a negative outcome. But as these other cars are moving, is that you end up, each car has a different cruise control. So this one is trying to maintain about 68 miles an hour, but it has the freedom to speed up a little bit and the freedom to slow down a little bit. And it has the freedom to change lanes. And so this is the foreground simulation. This is the real-time simulation. I'll show you. We also have in the background all the other cores of the processors that are in the cluster are running the same thing but faster because they're not constrained to the time constraints. Yes.
You mentioned how each car has a information about the state.
Right.
So that is we get where we at the end.
Yep.
So the outcome is that not slowing down, shouldn't be about slow down because then the car knows the information about the car behind that it shouldn't slow down.
Well, actually, we don't know the information in our simplified view of the world. Just to keep the state space reduced. our car actually is not looking behind us. It doesn't, and so it's looking at the car in front of us and not trying to not rear it, but it's not looking behind it to avoid it being hit from behind.
When you change lane,
yeah.
what you need to look behind you.
Well, so this is, when you change lanes, these sensors are telling you whether or not the lane is clear. And so it's using these inputs to decide whether or not you should change lanes or not. Again, in general, you would have a range of values, and so if you discretize this, you could add more states to have better resolution to what's around you. Yes.
Doesn't the key value store give knowledge to the model about the car behind it?
The car behind it knows how far it is to this car.
Sure,
so, yeah.
But the model, like on the cloud, for example, since it's actually called a key value store, isn't it able to know which cars are next door to each other, so to speak?
Okay, there could be a global solution, but we're not solving it that way. Okay. All the cars are operating autonomously, where they're only using the information they have around each other to do this. So yes, you could create a global algorithm to orchestrate how all the cars move, but that's not what's happening here. So all we're doing is...
That was the part that I was confused about before, whether your cars had knowledge of each other's states, so to speak. So I guess, yeah, not.
Right, yeah. They do not, the cars themselves, when they're making decisions, don't have access, aren't using that as part of the inputs to the algorithm.
Okay.
You're right, the key value store has access. Those are stored in the database so that we know how to render the cars into the global state. But as we're doing learning, we have to learn with the information that we have access to. Right. So it's not, in driving, it's not, the cars generally don't have access to what's going on way down the road.
Sure. You might have, like, as a driver, you might have an idea of what cars are surrounding you might be doing.
Yeah. Right. And I think that as we have smarter cars, that'll happen. Is that it'd be nice if the car next, like for example, this does not take into account a range change indicator.
Yeah.
Which right now is a blinker, but in the future it could be a signal from the car nearby that it intends to transit into that lane. That's really useful information for a car to have because you don't know if this car is going to change lanes. It does. It hasn't told you unless it indicates that. So if we kind of build smart systems, having more inputs like that would be really helpful. Yeah. So we talked about the actions, the states, So what this system, now kind of getting into the nuts and bolts of the system, so this is what this is running on. So this was a rig that we took with us to the last supercomputing conference in Denver. And the system was a 1U compute server with Intel Xeon CPU and an FPGA card. And so an Ethernet switch that connects us together. And so the model was that we had a display client, which is what we're just looking at, which was just a Chrome browser. And that Chrome browser is running JavaScript to pull data from the key value store to display the full state of the world. That's why you can see all 30 cars on the screen, is that this is pulling key value pairs that have all the state, the state of all the cars, where they're located. And then on the FPGA, the key value stores were distributed across 2 FPGA cards. So this actually is the Intel PAC card, which is David's. It's a David's project at Intel was making this new Intel PAC card with an RDF 10 available, and so that's one of the platforms that you can run key value store on. This is another vendor card with an Altera FPGA Stratix 5, and this is the 10 gigabit Ethernet port on the card. And so the key value store is the read requests for a key come in, get processed either by local memory on the FPGA or by the DRAM around the FPGA, and then get serviced back to the compute server that asks for that data. And so the compute servers are just threads running on Xeons that deploy in state from the KVS, running the simulation, and then when they have a good outcome, writing state back for updating the Markov model. And with the KVS, you can hash out, instead of having all data get written with one card, you can load, distribute, do traffic across multiple cards. And then all of this is being tied together through just the standard Ethernet switch. So this is the topology that was used for this. And so this is a more picture of the physical system. So this is the Ethernet switch. So these are 10 gigabit Ethernet ports with fiber SFP plus connectors. And so these fibers are connecting to a NIC that's inside of the server, as well as to the FPGA cards that have the 10 gigabit Ethernet ports with the key value store. So it's just physically having multiple of these cards in the servers and having server connected to the switch both through its NIC port as well as with the FPGA port. So all the traffic is going over the Ethernet switch. And then inside the server is the FPGA card on the left, the CPU under the heatsink in the middle, and then the 1U rack chassis that holds it all together. And then the dashboard is what's running on, and this is actually an Intel i7 with the graphics output. So this is just running a 4K display that's pulling into state. And in addition to what we saw with the display screen, it also has some stats and analytics of the processing, which is keeping track of how long can the system go without having an accident, which is this chart. How busy is the key value store? How many hundred thousands of KVS operations are happening? And then also these parameters that you change. How many parallel slave machines do you want to have to do the training? So the more the better. It's faster that way. So this is after about 7 minutes of training, or a few minutes of training. Same setup, but with a little bit, the Markov model a little bit refined. And so it's not perfect, but it's better. I'll let it run for a second. You can see the car is a little bit less erratic. It turns out that changing lanes all the time is not a real safe procedure, especially if you don't know. Nobody uses signals in this. Not perfect. That was a rear end accident right there. A little dangerous to do a high-speed braking on the highway, but you'll learn that because if you do it a few times, that you'll get penalized in the state machine update. So again, this particular car is trying to maintain a cruise control speed of about 65 or 66 miles an hour. Which right now is in a pretty good state around these cars. It looks like he's trying to get around those three that are walking right now. So this is running longer. As you can tell, the biggest thing is that it's running longer without an accident. And so, again, that car just got out of the way, he accelerated. He's finding a solution on how to speed back up. So now he's trying to maintain close to 70.
Is he actively penalized for not maintaining his better speed?
Yeah, so the goal is that the part of the reward function is to maintaining your speed is the variable. And so anyway, as these run, the other stats screens are keeping track of how many simulations ran to completion, how busy was the key value store, how many insert operations, how many times we modified, was the total activity. And so that this was just with 2 servers running that were pushing hundreds of thousands of I/O operations per second. But in general, as you'd run dozens of servers, you would end up getting to millions and potentially billions of I/O operations as you're stressing the key value store. And so the activity that's going on in the key value store is the Markov model. It's a single process that's reading the simulation results and rewriting the policy actions. And then the simulators that are reading the policy, writing the simulation results, and then real-time analytics, which is what's showing us the dashboard. So all that data is being fed out of the system. So the next thing I want to do is just go a little detail about what this key value store is. Why did we do it in FPGA? What made it different? And so one of the biggest differences of offloading compute to an FPGA is speed and latency. And so we did an implementation of the key value store in software on a Linux system where basic operation is you get a query that comes in as a packet, and it says, I want to find a value for this key, and the system goes to memory, and it finds that, does a couple hash functions to find that value, and then it formats that response back into a packet and sends it out over the network. And this is the most traditional way to write software for doing networking is with Berkeley sockets or BSD sockets. And so, which is just opening a UDP socket to read and write. And on a Linux box, modern processor, i7, the time it takes to read a packet in, do a couple hash operations for the key value store, pull a value out of memory, and write it back over the network, averages turned out to be about 41 microseconds. And so this is a distribution graph that shows for a couple million runs of the key value store, when you run it in software on a standard PC, is that it's not always 41 microseconds. It's on average 41 microseconds with a distribution curve. And so sometimes a little faster, sometimes a little slower. Standard deviation about 10 microseconds, which is the width of this curve. And you can see there's some outliers. And so this is a problem. If you're doing a self-driving car, one problem with the outliers is that if your underlying database has an unpredictable response time, then how do you know that you're going to be able to make a decision if you can't even read the value out of the database in a constant amount of time? And so we cut this chart off. Actually, there are outliers that go further. But you can see how in software, what gives rise to a lot of jitter, which is time variance, are things like having cache lines. And so sometimes when data is cached, you hit the L0 cache, or the L1 cache, or the L2 cache. Sometimes your processor is doing other things, and so there's context switching. The operating system periodically is doing cleanup tasks. And so when you run networking applications in software on a Linux system, this behavior is very typical of having a pretty wide distribution of time in terms of how long it takes for things to happen. So the first optimization that you can take in the data center is to get rid of the operating system. Is that rather than pass everything through Linux, what if you just directly let your CPU pull packets off the wire and process it? And so this is called kernel bypass. You bypass the operating system and you let your hardware, your CPUs, directly read from the network. And this is a technique that some of our customers that do high-speed trading learned many years ago, was they bought NICs that did kernel bypass. And you can see this is a drastic difference, going from 40 microseconds down to single-digit micros. There's like an order of magnitude improvement in how long it takes to read a value off the network. That is that when your network I/O speed is the bottleneck and you avoid the operating system, you pick up a big gain. And so that's the gain that was picked up by kernel bypass. And so this goes by a couple of different names. With Intel, BPDK is a library that provides this kernel bypass. OpenOnload is something that another vendor uses to describe their kernel bypass approach. But you can do better. And so going one step, so this is pretty much single-digit micros is the best that an i7 or Xeon, the best that a CPU system can achieve with a 10 gig NIC. But if you offload the whole function to an FPGA, there's another order of magnitude to be gotten. And so this is the latency. When using the FPGA to do a key value store, the kind of the minimum, maximum, average, all pretty much converges to a couple of clock cycles. Because you build a hardware data path where you know exactly how many clock cycles you read the value in, you hit a memory, you get the response back, you hit another memory, get the response back, do it a third time, format the packet and put it back, is that it's a deterministic pipeline. And so by designing the hardware data path, you can be very precise about how long it takes to do something. And so if you look at this distribution chart, it's basically an impulse function on the chart. Is that almost all of the times are either this clock cycle or that clock cycle. It's about 50% of the times are within 6 nanoseconds of each other. And the only outlier is that there's one or two where the phase of the clock was slightly off in factor. And so this is almost jitter-free. I mean, that the time that a packet hits the Ethernet, the time the key value store responds, when it's pointed out of SRAM, is that it's dead on. You know exactly how long it takes. And that's about an order of magnitude better than the best you can do with software, and about 100 times better than you would do on a typical Linux system. And so this is why we use the key value store. So the latency, I mentioned, about 10 times faster than kernel bypass, about 100 times faster than Linux sockets. Throughput-wise, a big improvement as well. It's got about 10x improvement in throughput, even when you have multiple cores running. And so typically in a data center, throughput is what drives cost, and so having a system that has 10 times better throughput means you can have 10 times more compute at the same cost. And also, if we're using power, we did a power per operation measurement where we measured the operation, how much energy was consumed by the system as we did database operations, and the measured results were about 10 to 20x reduction. So it's a lot more efficient if you can build hardware to do the function. The power efficiency is a lot better. And there's some other results that collaborate that as well. So Bob Broderson at Berkeley published a number of papers decades ago and compared from the early days of CPUs to ASICs what kind of power savings were available theoretically when you didn't have to move data around the chip. Is that if you could build a data path where when data came into the chip, it just went through the minimum amount of logic that was needed before it went out, is that his results were consistent, is that a lot of computations gained between 10 to 1,000x improvement in power by having custom data paths that were optimized for the compute operation. And so that led to things like DSP processors, accelerated math units, and so people know that building chips has benefits over microprocessors, but if you can have a programmable chip, putting a function into an FPGA still gives you a benefit on the order of, an order of magnitude or two. So there's some other applications that could use this model. So we just looked around on some other things that people do with MDPs, and we're wondering whether or not that doing the real-time analytics with the key values sort of be applicable. So things like in transportation, that the markets of airlines, Uber, taxi, fleets that could benefit from low latency, high throughput power. Banking, our company Algo-Logic actually does quite a bit of fintech, and so we do things with making trade decisions in real time. So this key value store is used as part of that system as well. But as we're deciding how to do stock trades, and reacting to market data events, we maintain databases of recent activity and can pull it out of the FPGA very quickly. And so other applications like web services, weather forecasting also make use out of, have been sped up with the MDP as well. Some of the interesting applications, connected cities, is certainly something that's growing. We see sensors being deployed now that are collecting all sorts of data from telephone poles and from devices and cameras that are being deployed in cities. Having machine learning to pull in and make use of that data, the real-time analytics that come in could be really interesting. And so, anyway, that's the short of it. So, Algo-Logic is that we're a company here in Silicon Valley that we mostly focus on putting things into FPGAs, but we had a chance to experiment with not only using the key value store to store the data in FPGAs, but also put an application around it for machine learning, and came to appreciate that with the machine learning system is that at least on the highway, that within a few minutes, a small cluster of computing was able to figure out how to drive in what took me months to a year or so when I turned 16. So by the time that system simulation turns to about 7 or 8 minutes, it's driving pretty much collision-free with a lot of the same use cases. So, any questions? Yeah.
How large is the company? How many employees do you have?
Yeah, so 20 people about is that. So the company started 8 years ago, and so after, as at Stanford University, is that we had we're using the FPGAs for a bunch of research projects. This project called the Net FPGA had been deployed out at about 1,000 universities or 1,000 users at universities, mostly graduate students were building kind of science projects around this networked FPGA platform. But we started getting some interest from some companies. And so companies like Agilent, for example, was interested in pulling in data from antennas. And Google was interested in doing MPLS switching. But most interesting was that we had some trading companies that when they saw the latency numbers that we had, asked, could we trade at that speed? And they started building applications that could trade with an FPGA. And they were able to beat software systems that were doing the same trading and profit from it. So then the company started kind of out of necessity because we started having our graduate students doing things that look a lot like building products. And having customers, I joked is that as a graduate student, if we got something to work 9 out of 10 times, that's a huge success, right? I mean, that's, as an academic, is that pretty much proves that what you've done works. But in industry, that's called 1.9. It works 9 out of 10 times, and they want like 5 9s, like 99.999%. And so part of what we do is a bit more testing. And so it's kind of an applied science of not just trying to get it right one time, but also making sure we hit some of the edge cases. So yeah.
Have you guys done simulations with more like real-world latency issues, like in self-driving cars, for example, like they'd be operating in a wireless network that would have much longer delays between, sending state values to the compute server and compute those, and whether that affects, how long it takes for the system to train, so to speak.
Yeah, that's a good question. No, for the self-driving cars is that, but very relevant question is that if you want to model different types of delays that you get from your sensors, like one interesting factoid is that GPUs get used quite a bit for doing image processing. But one dirty secret of a GPU is that the way that they achieve performance is by having a deep compute pipeline. And so in many cases, your GPU might be processing several images behind what was just collected by the camera. And so what you see is not where you are, it's where you were 5 or 10 frames ago or more. And so if you're doing modeling, you'd want to factor in, your model has to factor in the fact that it's got this inherent delay in some of the sensors. So yeah, it's good. Yeah, question? Okay, yeah. Okay. Yeah.
So you're not using any, you're not like importing a data set. It's not machine learning, it's not like AI in that sense, right? It's more of like a optimization, right? Like line optimization. So how would you, could you apply the same technology to something that doesn't have any kind of trend or like an example that comes to mind is like maybe a market, like an undeveloped market that doesn't have a history, like a very predictable path as to where its price rises and falls. How would something like this respond to like very dramatic changes in the market?
Yeah. So are you considering a case where the environment's changing, and so that you have different solutions that form over different time periods, or?
I guess I'm thinking of like maybe like a stock price that like opened just a few days ago, for example, and it has dramatic inconsistencies.
Right. Yeah, I mean, trying to look at time history of I would say a stock chart by itself is pretty stochastic. Is that it's really hard it's my experience, because we've been working with traders now for 8 years, but use this, is that the high frequency traders aren't making money by watching one graph. They're watching money by watching multiple correlated graphs, and some of the data that they're watching are leading indicators to the other. And so that's where the latency game comes into play, which is, say you're trading futures, say you're trading Bitcoin, as this question came up with, and you've got a Bitcoin price in the US, you've got a Bitcoin price in Korea, and they're a little bit different. Well, they'll probably converge, right? It's that in steady state, the world will come to a point where if you can buy a Bitcoin for $8,000 here and sell it for $7,000 there, you'll do it. And so some of the types of ways that you can do high frequency trading is watching multiple markets and being the first one to equalize those markets. Because it's a guaranteed profit. It's that if you know that the coin is 8,000 here and 7,000 there, then it's not just a guess that you can make that profit, but it's a guarantee that I know I can do that arbitrage.
So it's a viable market to sell in very quickly.
Right, you buy and sell, and so so it turns out that in many cases it's not just about the computation, but it's also about the communication.
Right. And
so not in this presentation, but in a different one, a colleague just presented. He showed how, like for example, trading between the U.S. and Europe is that the information, let's ask this. What do you think the fastest way to share information between the stock exchange in New York and the stock exchange in London might be? Now take a guess. Imagine it's going over a network like the internet, which is pretty much how stock market data goes. But just what path do you think that information would take on its way between London and New York?
Probably many alternative routes. It wouldn't be a straight path, or if you'd have to,
Transatlantic cable.
Yeah, that's a more traditional answer. Is that
Is there a microwave link? Too far away, right?
okay? Right. So transatlantic cables first, and so most volume of traffic going between continents is going under sea in a fiber. And for microwave, you're right that microwave gets used in between cities where there's line of sight, but unfortunately, because the Earth is round and Europe is so far away from the U.S., is that you'd have to go through this part of the Earth, the circumference of the Earth. So microwaves don't work for that. One interesting factoid, though, is that how fast is the speed of light?
3 times 10 to the 9.
10 to the 8, yep. And so how fast, now, that's how fast it is in a vacuum. How fast is it in the air?
In the air, it's almost right.
Yeah.
In the fiber too.
Exactly. Right. And so that when you, the reason that in the air, the index of, whether it's a vacuum or air, it's still about 1. And so that the speed of light is through the atmosphere is pretty close to the speed of light in a vacuum. But glass is far different. Glass has an index of refraction of 1.5 instead of 1. And so C, remember the N factor, you divide by 1.5 and it only goes 2e8 meters per second. So right there, that means that when you send data over a fiber network, it's only going 2/3 the speed of light. And so the point that came up is, what if you use microwave? That's an advantage if you can use a microwave, because the microwave is going at pretty much the full speed of light versus 2/3 the speed of light. And that's something that gets used for trading. Here's another interesting question. So you might say, what about a satellite? What's wrong with a satellite?
it's not a
You're jumping ahead, okay? That's correct for low Earth satellites? They're always moving, but for most traditional satellites that are geosynchronous, what's the problem with them?
They're very far away.
They're very far away, right? So your path, even though you're going to the speed of light, you're going out of the way by a very large triangle. But so why go so far? What if you had a low Earth satellite?
That's a much more.
And so building networks of low Earth satellites give you the advantage if you don't have to go as far. But the disadvantage of the fact that they're always moving. And so what's the latency? You can predict the latency for a static system, but if things are moving, their latency, that jitter calculation is going to be variable. That's just a complication. Anyway, other questions? Yeah.
Thank you for the great talk.
Yeah.
There was recently a fatal car accident where Tesla autonomous mode was involved.
Yeah.
So what's your opinion about the future of driverless car?
Yeah, so, okay, great question. So I was actually on Highway 101 South. My commute to San Jose to our office takes me down Highway 101 South every morning from Palo Alto. And I would have been about 15 minutes behind that Model X car that had an accident on Highway 101. And so suddenly all the traffic, the GPS went red. All traffic paths going south became blocked. Looking ahead, 3 helicopters appeared on the skyline that were currently hovering over where the accident happened. And about an hour later, I was able to finally get past the one lane that was still open and look around to see what had happened. And what I saw there was half a car. Is that I saw a Model X that had been effectively cut in half because it had just run at full speed into a concrete barrier. And it killed the driver. The driver was an Apple engineer on his way to Cupertino that morning. And apparently his car was in self-driving mode. And it had tried to warn him that it wasn't quite sure what was going on. So Tesla is a semi-autonomous car. And so when it's not sure what to do, it'll jig the steering wheel, an audible beep, a visual alarm will head off. But this is only speculation, but it's been speculated that the driver of the car might have been looking at his iPhone But it was certainly, according to the log that was recorded on the car and that was recovered by Tesla, was that the car had definitely been in autonomous mode in about over 100 meters before the accident. I think several hundred meters, had given alerts to the driver to take control of the car that were ignored. And it proceeded to...
100 meters, how many seconds is that?
It was...
Yeah, when you're driving on the freeway?
It was a reasonable amount of time. It was several seconds.
6 seconds.
Yeah.
Yeah.
Yeah, actually, just because this topic was kind of near and dear to me, you bear with me for a moment.
Anyways, the answer that you're saying is it's your fault if your car tells you to sync over and you don't manage to, so you better stay alert all the time, right?
So well, there's different viewpoints on that. Is that Google has a division called Waymo, and they take a slightly different view of what an autonomous car safety should be, which is this belief that the car should be over-instrumented with LiDAR, multiple cameras, multiple sensors, and be very conservative to a point where, by design, you don't have a driver. You don't expect to have a driver in the car. And so that is the philosophy that, and it's understandable for a big company like Google that has deep pockets, that when they have an accident is that you can be certain someone will get sued, takes a very conservative approach. As opposed to Tesla, a little smaller, a little more scrappy of a company, where Elon Musk's view is that if your self-driving car is safer than a human, then probably using the car in self-driving mode is better than having a human drive it because it's less likely to have an accident than a human. So the what is the right threshold for this self-driving cars is that they're already safer than humans. Like, I mean, I'm not claiming our system is the best, but...
There was a really interesting article about that recently in Australia, and if you take average humans, that may be true.
Yeah.
But the car accidents are extremely strongly related to intelligence.
Okay.
So if you're a good driver or a bad driver,
right.
Yeah.
Right.
That's an interesting...
It's a wide distribution. Yeah, it definitely is a wide distribution.
Yeah.
And so...
I mean, making the car safer is, of course, the goal, right? Do you think that you will ever be able to use self-driving cars and humans in the same way?
Yes. Yeah, because my commute, I have a couple pictures on this. Is that just yesterday, as I was driving in traffic, I had 3 Teslas around me. All 3 cars in front of me on Highway 101 South were other Teslas. And so, and I'm guessing that probably all 3 were probably in self-driving mode. Although I hope this driver's being a little careful because that was the same place where the accident happened a month ago. There's been a firmware update since then, I think. But still, is that it's just common occurrence right now in Silicon Valley to have, Waymo has their cars mostly around Mountain View, and so you see the Waymo cars all the time. You see Teslas everywhere. Is that it's not science fiction. Is that it's commonplace now in of having these self-driving cars, and so one of the interesting questions is how do the self-driving cars interact with humans, right?
Yeah. How do you experience that?
That's a really good question. I think you could run simulations one way, is that you could have, human drivers and you could have different AI algorithms that interact. But I think it'd be interesting if, I would guess that the way that a Volkswagen AI might work is going to be a little different than a BMW AI. And so the BMW AI is probably a little bit more aggressive on how it's going to be driving on the highway, but that may be fine when it's dealing with other BMWs, but what happens when it comes up against the Volkswagen? Will it factor that in? Will it take into account that maybe this car is less likely to make a sudden lanes change and speed up? Who knows? Yeah.
We think there's an application for computer technology in vehicle network, for example. Say, we have the traditional CAN networks for all the traditional sensors, but then with the autonomous cars that have LiDAR and computer vision, we might be operating more traditional compute systems and using a traditional computer network. We see an advantage of using FPGAs in that type of setting in order to lower latency
No, I think that's definitely valid. Is that like CAN networks are used quite a bit in automotive,
Right.
but they're not very high bandwidth.
Yeah, they're low bandwidth, and you have to have many annoying, still sensors.
Right. And so other types of sensors, a lot of traditional sensors like accelerometers and ultrasound, they have what are called SPI buses, or I2C. One kind of neat thing about an FPGA is that you can program a state machine around every I/O pin to drive like an I2C bus or a SPI bus. And so like one FPGA device can be pulling data in from hundreds of sensors with a state machine, guaranteed latency in time, as opposed to a software gateway, which might need to be time multiplexing between all the different sensors. Also, I think the questions are there is industrial Ethernet that has some real-time guarantees for packets, but even a 10 gig Ethernet, if it's switched, is that as long as you rate control the flows, you can still come up with bounds on how long it takes for packets to get through. And I think that you'll see, especially in cars where you have dozens of cameras, which is reality, and LiDAR, is that you're going to have to use 10 gig Ethernet and networks like that as part of the solution because you've got so much data to pull in and move around. Yeah. So, yeah.
Let's say we run vehicles in the highway on this the network.
Yeah.
Or in all we can access the key value.
Yeah.
Have you ever, are you going to look at in the future, or have you ever looked at to the case where you have vehicles which are not in the network?
Right. So we would envision for the driving part of the operation is that the car itself would have the key value store would be an internal network to the car, and that it would be pulling data off the car and not relying on the internet to drive it. Because if there we go.
Nothing giant security concern, right?
Yeah.
If you have an external driver of the car,
Yeah.
then you have a malicious or even accidental malfunction. That's a giant disaster, right?